Okay, thank you everyone for being here. Welcome to this presentation. So today we're very happy to have Jasper Ruth, and his presentation is about a sandwich with water, Bayesian frequencies uncertainty quantification under model misspecification. So take it away, Jasper. Thank you for being
Thank you.
here.
Thank you, Lela, for having the opportunity to present this work. I remember volunteering about 4 months ago. I asked Lela, hey, do you still have a spot? And then she said, yeah, I have August 14th. And then I completely forgot about it. And last week I got a reminder that I had a dentist appointment. I wanted to put in a crown, and I've been trying to push that off for months. And got back from a cruise, had COVID, was supposed to do it then, told them I had COVID, said, okay, we need to postpone. So anyway, I had just had my appointment at 8 a.m. and the dentist was a little skeptical that I would be able to present. So if I say a lot of strange, unusual things, then just let me know. You can always write an email. But anyway, point is, I feel it's a little difficult to talk and let alone think. Anyway, so thank you so much for being here. So I'm going to talk a little bit about something that has captivated my interest for at least 20 years. And that is, what do we do when the models that we use, the theories that we use, are imperfect? What do we do in terms of inference, estimation, prediction, forecasting? And is it possible that we actually learn from data? I would argue that we've learned a lot from data, but a lot of that has been done in lab experiments where we control variables. And those experiments give us insights into physical relationships between A and B. So that's wonderful. That's all in a lab experiment because you can control the boundary conditions, you can do a lot of measurements, etc., etc. But can we actually take data from the field, for instance, in hydrology, from a watershed, and then we have a model, and then we compare the model with the data, and can we then learn? Is there a way to really learn from that data? That we learn new physical relationships or physical laws. So that is the question that I've been really trying to understand and work on for 25 years, essentially. It was a question that was posed to me by my PhD advisor that gave a simple example. He said, in my PhD research, I ran into this and this problem that I think there's a compensation between model structural errors and parameter estimation. There's an interaction there. So anyway, that got me going. And I think now finally, after 25 years, I think I finally have started to make a little bit of progress. And that's primarily, I talk about this work that I talk about today. The funny thing is that some of this work has been out there for 50 years, but it's not picked up. It's even for statisticians. Most statisticians do not know what I will tell you today. Okay, it doesn't appear in statistical textbooks. It's quite remarkable. Plus, I will also show you that there's an inconsistency in statistics between the Bayesian approach and the frequentist approach. Also something that most statisticians are not aware of. So I start with, I gave this talk at HydroML, and just for the general overview, I start out by just explaining the bigger picture. This is a common slide. Hoshin has presented slides such as this, like going back 30 years or so. So I have a model, and let's focus on the parameters now. The goal, I want to get my model as close to the data as possible. That is a goal. That is not a very well specified goal, as accurately and as consistently as possible. But that is another story. So unfortunately, this whole process of trying to get the model to match the data is not as easy. And that is because we have all these sources of uncertainty. So, oh, no pen. I don't want a pen today. I want a laser. So I've obviously I have my initial states. Now, fortunately, in the systems that we work on, most physically based systems, most environmental systems, they have negative feedbacks, which means they ultimately converge to a stable state, meaning that the initial state is not that important because you can get rid of the initial state by using a spin-up period, okay? Anyway, if you look at the weather system, that's a different story. Then that's deterministic chaos. The results are very much dependent on your initial state, but that's a fortunate thing that we don't have. So the initial state is usually not that important if you look on, calibration, all that. Now, we have these uncertainties in parameters, the forcing data, and the material properties. And what I'm interested in primarily is the uncertainty in the model structural error. What is wrong with the equations in my, with the model equations, okay? So because we have all these sources of uncertainty, the comparison of measured data with model output is not as easy as we may have thought 40 years ago, okay? So Bayesian theory tells us we should specify a prior, we specify a likelihood, and then we yield the posterior here, okay? Now, we can specify a prior, we can specify a likelihood, that gives us a posterior, okay? We can do this. Now, we can even specify likelihoods which are distribution adaptive, meaning we do not make prior assumptions about the distribution of the residuals, but let the inference, let the data tell us what that distribution should be. For instance, this is what I coined a universal likelihood. And what you see here, that based on its distribution parameters called nuisance variables, it can take on many different distributions. Okay, so you can infer those nuisance variables along with the model parameters, and hopefully the inference goes okay then. Now, we need methods. Methods such as Dream can do this job, no problem. So essentially, we're done, right? We followed the statistics, the statistical steps. We have data, we have a model, we use a prior, we use a likelihood, we use an MCMC method, we sample, we get a posterior, we do residual analysis, we can do all these things. Yet, what you will find is that the structural errors in the model and the forcing data errors are so difficult to describe. Forcing data, rainfall errors, right, are so difficult to describe that it's really difficult to do this right, that you feel like something is missing. These errors, I cannot, even if my forcing data errors are perfectly Gaussian, my rainfall errors, imagine I draw them from some normal distribution. When they propagate through a model with memory, and hydrologic models are models with memory, right? As soon as Gaussian errors propagate through a model with memory, they accumulate, these errors accumulate in the state variables and come out as non-Gaussian errors. So even Gaussian, simple to describe errors can translate into a time series that is really difficult to describe, okay? So anyway, so this is the problem that I worked on. So the problem is that, forget about the input errors for now, okay? What I focus on is the model error. The model is never always perfectly true, meaning the assumption in this Bayesian paradigm is that the model that you use, the data that we're trying to explain with our model, that is perfect. And that we know that assumption is not true. That is an invalid assumption, okay? So, but then what do we do? Now, funnily enough, there is a field called M-estimation. And people in M-estimation, this is exactly what they have worked on for so long, okay? And M-estimation, the father of M-estimation is John Tukey, okay? And I mean, you can see that some people are really smart, because what you see in careers is that early on in their research, they figured out the culprits, the big problems, and they focus on those, solving those instead of doing the smaller side things, right? So very early on, he realized, 1962, he wrote a book, Future of Data Analysis, that these classical statistical inference methods, that they're extremely sensitive to deviations from the perfect assumptions. So in other words, if we have outliers, he calls wild shots, blunders, then the inference methods will not be robust. The conclusions you draw from your data analysis are not robust. They're very sensitive to deviations from the assumptions you made. So what he focused on, certainly early on in his career, is can we develop inference methods that are not as sensitive to deviations from those assumptions? Now, that is what M estimation has become. So, and Peter Huber and Frank Hempel, they're considered, the three of them are considered the founding fathers of M estimation. Now, I stumbled on this in my context when I was working on scoring rules, because I was looking at the limiting distribution of the scoring rule, and in the literature, they will tell you that is the sandwich distribution. And I was like, what is a sandwich distribution? That brought me to M estimation, and now we're here. So Peter Huber has shown, and I'll get to that in a little bit, that if you're in the field of M estimation, essentially M estimation is a generalization of maximum likelihood estimation. Maximum likelihood is one class within, or one small group within M estimation. Okay, M estimation looks at this general objective function. If you want to minimize that, this is the formulation. So I have an observation, I have a model prediction, I divide that residual by a standard deviation, and then I have a certain, I take a function of that standardized residual that produces an output, and I take the sum of all my data points, so 1 through n. So essentially I have a residual time series, I scale that with sigma I, so I normalize that, I feed that residual time series through a function called rho, and rho gives it, that's a scalar valued function, so that scalar valued function will then, you know, do that n times, I take the sum, and I'm trying to find, so that's my objective function, this, that I'm trying to minimize, okay? Now, you can decompose this objective function, and then you get things such as a score function, such as an influence function, and such as a weight function. And these three functions are very interesting to study because, for instance, the influence function, I'll show that here, will tell you, here, this is the influence function for a number of different estimators. And this tells you, if here is my standardized residual, which is the residual divided by sigma, right? So it tells you the contribution of that residual to the objective function you want to minimize, okay? So you see here, for instance, the least absolute difference objective function, that the contribution doesn't change with the magnitude of the residual. Okay, it's a constant influence function, and that is what you like to have. That's why it's known that this is an L1 objective function. That's why it's known that L1 objective functions are less sensitive to outliers than least squares, L2 type of objective function, because you can see that that influence function, the larger the residual, the more effect it has on your objective function. And that's what you don't want, because then outliers will really start to affect your objective function. You're trying to avoid that. So Huber, Hempel, they have particularly worked on defining a large class of these objective functions in such a way that the objective function is robust against outliers. Okay, so that is the M estimation. Now 1967, then Huber showed that if I have an M estimator, that I can also derive its limiting distribution. Okay, and the limiting distribution is what we'll get to, is the sandwich distribution, and that is fundamentally different from what we've learned in class. But for now, I want you to realize one thing, is that if we have a misspecified model, which is always the case, then let's say that this is our model space. Okay, this is the space that my model can describe. The true parameters of the data generating process are then outside my model space because I have a misspecified model. So these are the true values that created the data. This is this is 2 dimensions, right? But in reality, that's a high dimensional vector has many entries, theta 0. So the point is, it's outside our parameter space. We can never attain this value. It's not in our model space. Okay, so then you can have 2 situations. You can have situation A and you can have situation B. Okay, I'll skip that for now, but you have to realize that under misspecification, the true parameters of the data generating process are not in your parameter space. Okay, so let's look at a simple example here. What the consequences are of that. Obviously, we're all familiar, we're all aware what the consequences are. And for those coming late, I just went to the dentist, so I have major anesthetic numbness in my jaw here. So and it's affecting my brain as well. I'm see if I'm coherent or not. My wife used to say I'm not coherent anyway, but anyway, point is. Example here, what is the consequence of misspecification? Okay, imagine that my data generating process is just a normal distribution. That's the red line, okay? That's the PDF of my data generating process. Here you see realizations over time, sample number, and then the value, okay? I don't know it's a normal distribution. So what I assume a uniform distribution. So this is my prior. Okay, now I can do maximum likelihood on my uniform distribution, and you will see that this is the maximum likelihood solution of my uniform model. Okay, and why is that? I make A equal to the minimum observed value, and I set B equal to the maximum of the observed values. Okay, so this is the maximum likelihood solution. Now, the parameters of the data generating process are the mean and the variance, 0 and 1. The parameters in my model are lower bound, upper bound, A and B. So A and B have nothing to do with the mean and the variance of my data generating process, right? So A and B are outside my parameter space of the parameter space of the true data generating process. So our model is operating in another subspace, okay? So you need to realize that this is almost always the case, certainly in hydrology with pedo transfer functions, with the regionalization, all these things. It's wonderful if you find useful relationships, but in general, it's hard to find those relationships for a lot of variables. Okay. Now, you need to realize that the maximum likelihood estimates. So maximum likelihood estimates will converge to what I call theta star when you increase the sample size. So theta star is the best parameter values you can find under misspecification. Okay, Hoshin, you have a question.
Oh, I just wanted to comment that it's actually worse than what you said, in that in reality, we cannot assume that the data generating process is represented by a finite dimensional set of parameters. So this is a good example, but in reality, we cannot say that we have a data generating process that only has a finite set of moments. And so this is like an example that's easy for us to think about, but it's actually harder to think about the actual problem. Yeah.
No, you're absolutely right. I'm so foggy in my head. I'm sorry for that. So I may say some nonsense, but yes, you're right. In the best case scenario, the data generated process is something that we can capture in a certain dimensionality that is hopefully low, but yeah. So given the fact that we have misspecified models, the central question is, okay, what should we do? Because again, all the theory we apply on a daily basis, maximum likelihood theory, Bayesian theory, they all reside on the fundamental assumption that your model is perfect, meaning the model that you're using to describe the data generating process is at least sufficiently accurate. And we know that at times that's a questionable assumption. So do we then just throw all the statistics out of the window? No. We can do better. But
if I could just add one more comment about your very nice example, Jasper, if you go back to that slide, is that if the data really did come from that Gaussian distribution, then as you add more and more data, A will go towards negative infinity and B will go towards positive infinity, and it will never stabilize. Yeah.
Yeah. Yes. And this is such a simple example, but it demonstrates that the parameters are in a different subspace. It demonstrates that you can never converge to the data generating process. So it describes a number of problems that for most people, it's hard to think about. Because as you said, also that slide that I presented where you have the true parameters, you have your parameter space the model parameter space, because they're all high dimensional. The curvature, all these things are really difficult to think about what that means in practical application and how that changes theory. What I can tell you is that when we have an M estimator, and maximum likelihood again is an M estimator, then Huber, 1967, has shown that the limiting distribution of that M estimator is the sandwich formulation. And here is your sandwich formulation. Okay. In my paper, we derive all this stuff from first principles. I don't know if people appreciate that in hydrology. I argue that to really understand what is happening, it's important to understand that in detail. But you can skip the paper, the first 45 equations, and then you can move to section 3.1 and then see the application. But the important is that you see here a product of an A, a B, and an A matrix. That's why it's called the sandwich formulation. Think about B as a meat matrix, and A inverse A is a bread matrix, okay? That's why it's called the sandwich formulation. Now, what is A naught, A0? That is the negative of the Hessian matrix divided by n. So we have n data points, okay? In principle, you could construct a Hessian for each data point. So you could think of this as the average Hessian for n data points. And then you put a minus in front of your Hessian. So A naught, negative of Hessian divided by n. And then the B naught is the variability matrix, okay? So also called the variance of the scores. So these two matrices are very well known, okay? Now, if we look at this sandwich formulation, then unfortunately, how do we estimate? That's the question. How can we estimate these matrices for our MAP, maximum a posteriori density solution? How do we do that? So we need a sample estimate, right? So the statisticians make, they distinguish between a quantity, an estimator of that quantity, its theoretical definition. So here you see, this is our estimate of the variance of the parameters. That is the left-hand side, essentially. And now we have two formulations. We have what's called the naive variance, and we have the sandwich variance. Ocean, you have a question?
Just to clarify, your GW is essentially your first derivative, right? It's your Jacobian, the normal way we think about things.
This one?
Yeah.
This is the gradient. The gradient is the first derivative with respect to each parameter.
Okay,
so
so
sorry, now that is the derivative of the objective function with respect to each parameter.
Correct. So that's the product of the Jacobians. And
No, the Jacobian is different. This is the gradient. Okay, so that's the derivative of the objective function with respect to each parameter. The Jacobian is each measurement individually with respect to each parameter.
Correct, sorry. Yeah. Okay. But this is, B is what is very often used to approximate the second derivative in optimization methods.
Yes, yes, yes.
All
and
right.
this is, yes.
Yep.
Yeah. Yes, exactly. So these matrices, that's the interesting thing. Once you know this, you start to see how these matrices are used in different fields and in different contexts, people not realizing that it ultimately all ties back to the assumption of a perfect model. That these matrices come back in different formulations. And the point is that if your model is correctly specified, then these two formulations are identical. Okay? So I say that again, because I can show you my paper here. Here it is. You can see this, right? And here we derive everything from first principles, okay? So here you have your gradient matrix, derivative of the likelihood objective function with respect to each other. But here we derive everything step by step. So I'll stop here. What I'll tell you now is that in the case that your model is perfectly specified, correctly specified, then these two formulations, you compute them differently, but they will give the same result. Meaning that inverse A naught times B naught, in that case, will become an identity matrix. So this will cancel. And what you have left is that your naive variance is 1 divided by n times an. A is the sum. An is the sum of the an is the average of the a's over n different samples. Okay, we call that here in is the Fisher information. Okay, so this is the formulation that we learn in school, and this is the formulation that we use to compute the diagonal, your first order approximation, your variance estimates. In the case, and again, this is only true if your model is correctly specified, because then A naught inverse times B naught is an identity matrix. In the case that your model is misspecified, these two matrices are no longer equal to each other. Meaning their product here is not an identity matrix. So you need to work out that entire product here. And we call that the sandwich variance. Because you see that multiplication here, that this is the meat matrix and this is the bread matrices. Okay? The inverse, instead of calling the inverse of your naive variance the Fisher information, this is called the Codembe information. So under misspecification, and that's the scenario, the regime under which we're almost always working, we should talk about the Codembe information, not the Fisher information. Go ahead, I saw there was a question. Peishi?
Oh yeah, so I have a question. Could you tell more again what's the difference between A null and AN?
Okay, so let me 1 second here. Go to the, okay. So maybe I can go to the paper, it's easier. It's been a while that I looked at this. Let's see here. Oh, man, here we give definitions here. Here, this will do for you. So we start with the likelihood. So we write the likelihood. Let me make it even larger. I won't go over all of them in detail for those that think, oh, this is too much, but this is how we write likelihood of a single observation. Okay, so we have an n record of data, then this is the likelihood for n data points. And this is the log likelihood. Then the score function, this one, is the gradient or is the derivative of your log likelihood with respect to each of the parameters. So that's a vector. This, the one Hoshin asked about, is a d times 1 vector of first order partial derivatives of the log likelihood with respect to each of the parameters. Then the n times d Jacobian matrix stores the score function, this one, at each individual observation. And then the Hessian matrix here is the second order derivative of the log likelihood. Okay, so you have the second order partial derivatives with respect to theta. So this is your definition here. Now, so that is your A matrix essentially, okay? Here it is. So that A matrix is called Hessian, but also called sensitivity matrix. Okay? And then this B matrix is what is called a variability matrix. And that variability matrix also is here. That is the vector outer product of the score function with itself. This is a vector outer product. So this was a d times 1 vector, right? So we get a d times 1 vector times a 1 times d vector. So we get a d times d matrix here. Okay.
Jasper, you missed the thing that would have answered Peishi's question. If you go back to the other page. At the end of line 5, A0 is the limit of AN. Peishi?
Yeah.
That was a question that Peishi was asking.
Okay, yeah, I'm so
A0
fucking
and
mad. Maybe that, Peishi, was that your question?
Yeah, so my question is, what's the difference between B null and Bn and A null and An? I realized that An and Bn are calculated from the gradient or the second order of the gradient of the objective function. But what is A null and B null when you show in the first line of the?
So their probability limit.
What is PLM?
That's a probability limit. That means when your sample size goes to infinity, what is the expected value of that matrix?
Okay. So that is regardless of what objective function and the model structure look like, right?
Yes. So,
Okay.
yeah. So, so you need those two matrices. So those are just, if your sample size goes to infinity, what is the expected value of the variance of the score? What is the expected value of those Hessian entries? We call those probability limits. That's just for large sample size. So, so I started working obviously with statisticians, and they distinguish between a sample, between an estimator, between its theoretical counterpart, etc., etc. Those are all more or less the same quantity, but they all have a different notation. And that is a very interesting. For instance, in most papers, we do not distinguish between the variance and a sample estimate of the variance. We both use sigma square. Whereas in reality, the variance is sigma square and the sample estimate of the variance is S square. Okay, so it does give some additional insights if you do distinguish between those quantities, because sometimes we can define a quantity, but we can never estimate it accurately. We don't have a good estimator. And that's certainly the case in hydrology. So the key take-home message is, and once I clear out in my head, I can probably explain it better, that in the case of a perfectly specified model, these two quantities, the sensitivity matrix and the variability matrix, those are identical. And I'll show that in the case study. That is going to be true when your model is perfectly specified. If that's not the case, meaning you have structural errors or input data errors that look like structural errors, then those two matrices are not the same. And then you need to work out this entire product. And this has really important ramifications. So forget about Bayesian information. You need to think about Codembe information. Now, I'll create to get some understanding of that A and B matrix. Pesci, go ahead.
Yeah, so could you go back to the previous slides? So when you say that when the model is perfect and that there's no error in the data, AN and BN is identical, it is also regardless of how many data samples or observations you have. Basically, A1 equals B1, A2 equals to B2, and so forth, correct?
So for every observation, individual observations, those two matrices don't have to be identical, okay? But if you take a sufficiently large sample size, you'll conclude that those two matrices are the same. They can definitely differ for individual observations. Yes.
It's A naught equals to B naught.
Yes.
Okay, got it.
Yeah,
And could you say a bit more about the Godam information matrix?
Yeah, so we're used to the Bayesian information, right? Most of us are used to the formulation that it's the second derivative of the log likelihood with respect to each of the parameters, right? So partial square log likelihood, partial theta I, partial theta 2, or theta j. That is the definition of Bayesian information. Now, Codembe information is an extension of the Bayesian information where we left in that product here, essentially. That product does not reduce to an identity matrix, but it just stays in. So we have this formulation. That is what the Codembe information is. Yeah, we don't make the assumption that the model is a correct representation of the data generating process. You're talking about the 70s now, okay? 1975 or so. This is relatively new work. So I hope that does it for now. I'll give you some examples here that always, at least to me, always makes it easier to understand what's going on. So here, I create synthetic data, okay? So I have a synthetic rainfall time series. I just create some synthetic data, okay? Now I use the ABC model of Viering. That's a model, again, I'm very foggy in my head, so I forgot when he was in the 60s or so. So that's a simple equation with one state variable, the groundwater reservoir, and I have three parameters, A, B, and C, okay? Now, I can do some analytic calculations here, so that's why I did it. So the data is synthetic data, so I fix A, B, and C, I run the function, the model, and then it produces discharge, I add an error to that. That's my, I call that my observations. Now, what I do is I use my observations, right? I do maximum likelihood estimation. So I pretend that I don't know the parameters that created the observations. Instead, I use the observations that the parameters I know created, and then I use the observation again to backtrack or back infer those parameters. Now, I do that, and then at the end, I compare my sensitivity and my variability matrix. And again, this is over n data points, okay? Now, for what do I see? Those two matrices are basically very similar. They're, again, a multiplier of 100. You see the entries here, they look very similar, okay? So this suggests that I have a perfect model, which I have, because I used this model to create the data. Now, so now what I do, I still use the same data, the synthetic data, except I do inference with a rainfall record that has a 25% error. So the data record, the rainfall data record that I use to create the data is different from the rainfall data record that I use for inference. And now you see the result here. See, I have my A matrix. I refer to the B matrix here. I'll explain in a second what beta is. But you see, they really start to take on different values. And again, I have three parameters, A, B, and C. So that 25% error, that 25% error in the rainfall, even though it's additive, starts to affect the structural adequacy of your model.
This was random error on the rainfall?
Yeah.
Okay. Liling?
Li-Jing.
Yeah, thank you, Jasper. I have a question regarding on this rainfall error. So what I understand, this rainfall error is the data error instead of like the model error that we just mentioned. So the P is subjecting to some error in this case, right? So does that mean that this sandwich rule apply to both data error and model error?
So I guess I don't. So can you ask your question again? I guess I don't exactly understand again. Very foggy, so I'm trying to really pay attention. So you mentioned something about the data error.
Yeah. So my understanding is that the rainfall that's subject to 25% of error in this case.
Yes.
And that is the P, like the input error, but the model structure that you present here should be correct in this case, right?
Excellent
so
question. Now I understand. That's Li-Jing, that's an excellent question. Yes. So
okay.
15 minutes ago, I said, oh, now longer. Forget about the rainfall error, right? Fundamentally, if you have a perfect model, but you feed it with the wrong input data, then that model is going to be corrupted. And statistical inference cannot distinguish between input error and model structural error in the way we're doing it now. If you really want to distinguish between those two, then you need to have a lot of additional data of, in this case, rainfall, how it's spatially distributed. So basically, we cannot distinguish between those two sources of error. They both will, create models that are inadequate. And so in this case, yes, the rainfall is used to corrupt the model essentially.
Another way to think of it is that there's a missing component of the model which is describing the rainfall error.
Yes. Yes.
That's clear. Thank you.
Yeah, it's a good question. So by the way, the difference between beta, so you see a beta here and B. So you have to understand that once your model is misspecified, that beta or that B matrix is the variance of the scores, right? If you go back, it said the variance of the scores. Now, once your model is misspecified, you can imagine that those variance or those score values, those score functions, that they become correlated at different measurement times, that then covariance terms, like it's basically autocorrelation that you have in your residuals, right? Once you have a misspecified model, that you also will have in your scores. So you need to correct your estimator for the variance between the covariance between the scores. And that is why this is the difference between B and beta. They're the same quantity, but the way they're estimated is different. So this is an estimate that corrects for autocorrelation in the scores. Nevertheless, you see, it's still different. Now let's look at the effect of that difference on the parameters. So this is the naive uncertainty. Okay, for these three parameters. So if you do inference, right, we have the data, we do MCMC, or we can do first order approximation, whatever. And this is the sandwich variance in green. So you do see that the sandwich variance is somewhat larger. Okay, and again, this is only a 25% additive rainfall error. And most days it's even dry, so it's 0% error. And the parameters are chosen in this case so that the groundwater tank is dry at the end of it means 0 state at the end of a long dry period. So that my analytic solution, in the paper I derive an analytic solution for this model of the A and the B matrices so that it gives insight, so that you don't have to do that numerically, okay? But anyway, to derive those numerical or analytic solutions, it's useful if the state gets to 0 at the end of a dry period. Now, so the point is, if we relax the assumption of a perfect model, then parameter uncertainty increases. Here is the bivariate distribution. Again, this is only 25% error. You have the naive estimator and then the sandwich. Okay, so the sandwich estimator enlarges the confidence regions. So you have to realize that all MCMC methods that papers I published, all these confidence regions, all those marginal distributions, they're all naive estimates, all conditional upon the assumption of a perfect model, that if I would have relaxed that, the parameter uncertainty would have been much larger. I'll show that next. Hoshin.
So under the naive estimator, as n goes to infinity, the variance will go to 0. For the Godambi estimator, the sandwich estimator, that means that should not go to 0. The variance should not keep reducing. It should stabilize at some point.
That's an interesting observation. I need to think about that. But yes, that is what you expect. Then you understood theory very well, yes. So I need to think about it. I haven't thought about it. What I have thought about, Hoshin, is that the difference in the Codem and the Fisher information, that is a measure of model misspecification, that difference between those two. So in essence, that we're talking about the same thing here. Okay, so the next thing, we're almost done. I'm sorry for taking too long, but so the next thing I thought, okay, let's go back to a paper we just published and let's quantify then all this stuff. Let's look at the sandwich. Let's look at now. So I went back to a paper we published on that generalized likelihood, 14 years ago, the work that Gerrit Schoeps did. And then we extended that. So I went back to that paper from 2022. So what I did is I just took these distribution adaptive likelihoods, and I went for each of these likelihoods. I found the MAP solution, and at the MAP solution, I determined those A and B matrices. Okay, now after more work, this is the end result. So here you see for one of the likelihoods, you see the distribution that the MCMC method or the first order approximation gave. It's called the naive variance, right? And then you see the estimate you would have gotten when you've done the sandwich variance, okay? So this may seem as a small difference, but this difference is significant, okay? So you can see it better here. You see here the result that we always thought was correct. That is the blue confidence regions, the bivariate regions here. So you have all the parameter pairs. And now what you see is the sandwich estimator, okay? And the question is, how do I get the sandwich estimator right with MCMC? That needs a major theoretical adjustment of theory, because the sandwich, the MCMC converges to the naive. So how do I make sure that it finds the sandwich variance? Now that is, I'm working with some colleagues on that. So we found a way to enforce that. Anyway, point is that the sandwich estimator increases substantially the 95% confidence regions of the parameters. So going back to the clue method, right? I have some more results now, but what it shows essentially that there is a lot of justification to inflate parameter uncertainty, but now you have it based on statistical first principles. But basically the results that I show and have seen shows that when we do inference, the uncertainty in our estimates is much larger than we previously thought from first order or MCMC or whatever Bayesian estimates. The uncertainty is naive. It's underestimated because it's based on the assumption of a perfect model. We know that that's not accurate. If you explicitly recognize model misspecification, and your estimates become way more uncertain. This opens up a lot of additional questions in terms of methodology, because again, all methodologies rely on the assumption of perfect models. So we really need to open up a lot of these uncertainty, or a lot of these tools. Here I show you the 95% uncertainty, or also up to 99%. You see, this is conventional, and this is the sandwich. So I would say that this is at least 2 or 3 times larger, right? So again, all based on first principles, and that's what I was always looking for. Now, lastly, the nice thing of this is that we now also have a strictly proper scoring rule for model misspecification. This is based on work that Pauli did. And what he uses those A and B matrices. Here's the beta, again, is the corrected variant of B for autocorrelation in the scores. But he uses this as a simple metric for misspecification, but he doesn't use it that way. He uses this, what he calls omnibus scalar, to adjust MCMC sampling. Okay, so in the case you have a perfectly specified model, this is an identity matrix, then the trace of an identity matrix, now that's the sum of the diagonal elements, right? That's equal to D, the number of parameters. So if your model is perfectly specified, you get K is D divided by D is 1. So 1 is the optimal model. If K is smaller than 1, your model is misspecified. Okay, now you can extend this to a, here we present a nice metric. You can actually extend this, because Pauli's metric is not, it's a univariate metric. Okay, you should do this in all dimensions because you have deep parameters. And anyway, point is, you can use the Kullback-Leibler divergence between the naive variance and the sandwich variance. And you can work that out. If you assume that both of them are multivariate normally distributed, right? Then you can work this out, that it becomes this formulation where TR is the trace. I have the derivation in the 2024 paper on the scoring rules. Now, so then one related thing, and I know I'm over time. Oh, it's 10:55, perfect. In this new theory, and I've had these discussions with Keith Bevan now, I've shown him, he was very excited about all this. But the new theory shows that if you accept the Codembe information, you accept the sandwich estimator, and again, you should accept it, because that is theory, that's based on first principles. But if we accept that, then that has a lot of negative side things that we don't want to deal with. But anyway, but if we accept it, then the theory will show that that whole clue idea, that you raise your likelihood to an arbitrary power, the sandwich estimator will show that that absolutely has no bearing on parameter uncertainty. So you can raise your likelihood to any power, and parameter uncertainty will not change, because that power will affect both the A and the B matrices, and that power will cancel in that product. That's easy to show. Here you can see it already. If you raise your likelihood to a power lambda, then this is how it affects the variance of the score, and this is how it affects, the sensitivity matrix is how it affects the variability matrix, or the variance of the score. So here you get lambda, and here you get lambda squared. And what do you see now? If you do that product of A, B, A, then you have 2 times A, lambda squared, and you divide by lambda squared. So lambda drops out, okay? So that is for the sandwich variance, it drops out. But you see it does affect the naive variance. So let me try to rephrase this. The clue methodology, where we raise a likelihood to a power lambda, that is all consistent within the old theory, the naive variance. That shows that if you use a lambda, that you can inflate parameter uncertainty, okay? Because it's a way of reducing your Fisher information, okay? That's all consistent in the old theory. But in the new theory with the sandwich variance, that lambda cancels, meaning that power, you can raise your likelihood through any arbitrary power, but your sandwich estimator is not affected by it, because your parameter uncertainty estimate is not only determined by the variance of the scores with variability matrix B, but it's also determined by your A matrix. Okay, and that's where that power cancels. This is extremely non-intuitive, right? But you have the way to think about this is that your A and B matrices are two ways of estimating feature information. Historically, we assumed that both estimators would give us the same feature information, but that is not true. Okay, and that results in the sandwich variance. Anyway, I think that's it for me. Or yeah, here's the paper, and I think I will get it back from WR anytime. It's probably, you know, hopefully it's positive. Peishi.
Thanks for the talk. I have a couple of questions. So first, just to clarify, the sandwich estimator you mentioned is basically the M estimator. These two are the same, right?
The sandwich estimate, so M estimation is a separate field of maximum likelihood type of estimators. The sandwich is the limiting distribution of an M estimator. Again, you can have many different M estimators. I showed a few here, right? In the table, I presented a few. Those are all considered M estimator. Here, these things. These are called M estimators. Okay, here, there are more M estimators. There's about 50 or even more different M estimators. So an M estimate is a type of a maximum likelihood, a function you want to maximize or minimize. And of that function, of the limiting distribution of that function is the sandwich variance. So that is where the sandwich comes in. So they're not exactly M estimation, sandwich are not exactly equal to each other, but the sandwich originates in the field of M estimation, yes.
So then my second question is, in your opinion, what prevents the application of the sandwich estimator, which has been proposed a long time ago, being applied in, for example, in hydrology?
This is a really good question.
I think that might be related to another question is, what's the downside of using sandwich estimator, for example? Does that bring more computational cost?
Now, okay, this is an excellent question. So again, how did we stumble on this? It's putting together concepts from different fields. Then some people are aware of this. Why are they not using it? Because this is a very difficult message for, I mean, we have to really talk, we can talk about this for hours. There are multiple different things going on here, but the reason it's not used, people are not aware. Most statisticians are not aware of this. Okay, so even though they fakely know some theory on M estimation, they don't know Bayesian inference, or Bayesians don't know M estimation. Now, that is a reason most people are not aware. But the people that are aware, what is the greatest hurdle in widespread application? That is that standard methods converge to the naive estimator. They don't converge to the sandwich estimator. So the point is that all standard methods, we need to correct them to get the right result. And that is not obvious how to do that. So I now created software. I extend the dream with the trick how to do that. So we're putting that paper together for the statistics journal. But ideally what you want is have the MCMC theory, the detailed balance, for instance, ergodicity, that in that theory, it already builds in the possibility of misspecification. So you want your estimator to figure out whether it's a sandwich or a naive variance. You want the MCMC method to determine that. The way it is right now is that all the methods we use, they implicitly, there's an assumption of perfect structure, perfect whatever, and so they converge to naive estimates. So that's the reason people don't, they're not aware, but now there are some people are aware. The reason not to use it is that all methods they use, the built-in, they will converge to naive estimates. So we need to revise all those methods. That is, and that's what we're working on. We have the revision for the MCMC method that I can now make sure that it converges to the sandwich estimator. But that is essentially, Pesci, your answer to your question is why are people not, yeah, first of all, the message is out really short, right? But the biggest hurdle is that all standard methods are based on the old assumption of the naive variance. So they all need to be revised.
And you just mentioned that we can use the MCMC method to determine which estimator we can use. How to do that? Because, like, in my opinion, MCMC is a Bayesian approach, while the sandwich estimator is a frequency approach. So, are you suggesting combine these two?
Yeah, this is all, we already combined this. Frequentist, here, all these. So here you see the dots. That is the approximation derived from MCMC. And then the actual colored regions, that is the frequentist. That's a good question, by the way, I forgot to mention that. So this is a frequentist description. Blue is frequentist, the dots are the MCMC. So what you see here, that the MCMC gives us a naive description. Okay, you also see that here in the next slide here. You see here? MCMC gives us the naive, the dots are MCMC, the color dots, and the line here, that is the frequentist description. The line again is the frequentist description of the sandwich, the dots are MCMC. So we can modify MCMC to give us the sandwich variance, but it will increase the computational burden a little bit.
I see.
It is implemented in Dream now. I just have to release it, and we have to publish that idea in the statistics journal.
Okay, thank you.
You're welcome. Hoshin?
I think Li Jing was first.
Okay, Li Jing.
Yeah, thank you very much, Jasper. I just want to go step back and think about this problem better, because like the A inverse B, which is like ideally it should cancel out. But if that's like two different, then we know that there is a larger model error. So if we do not do that in the real world, we often compare the simulated data with the observed data and see how much those two are different. And probably that's the way to see the model error. So my question is, say if we assume a likelihood for the observation, and then we probably assume there is a larger model error. So the likelihood, we can change that a little bit because there is a large model error. So if we change that, and that will essentially inflate the uncertainty of the model parameter. So how that is different from the sandwich model.
Again, I'm trying to understand really your question, but basically I'm trying to look for a coherent statistical framework, right?
Yeah.
Because what you describe is, I'm trying to describe a generalized methodology, right? That will distinguish, that can account, or that leaves open the possibility that your model is misspecified and can deal with the consequences of that. And all the what you describe, it always resides on the assumption that your model is perfectly specified.
Yeah,
once
that
you
makes
start
sense.
to do inference, once you start to do inference, right? And going back to the question about model structural error, we need to really make progress with that, or in general, we need to account for uncertainty. And so in our uncertainty estimates, whatever we do, whatever inference we do, we need to account for uncertainty, acknowledge that our inferences may be subject to uncertainty, and then propagate that uncertainty, what that means for our conclusions. And so the question then is, how do we do uncertainty quantification in the presence of a hypothesis that we know may not be perfect, may not be the data generating process? How do we acknowledge, how do we move forward the structural errors? How do we deal with that in our estimation? By the way, what I do want to mention explicitly is that this is all nice and well, but a lot of people would say, yeah, Jasper, now you have a better estimator of the uncertainty of the parameters. But people would say is that in the case your model is misspecified, those parameters are meaningless. So how useful is it to have accurate estimates of uncertainty on parameter values that are entirely meaningless, right? You should look at bias, essentially, once your model is misspecified. Yeah. Anyway, that as a side note. So basically what I'm trying to say is that all the inferences we've done and what has been taught to us in school is based on it's predicated on the assumption that the data generating process is in the space of models that we consider. And that's
that's pretty clear. That's pretty clear to me.
Yes.
And I think when you do this presentation, I think about the model like if we have any model error, and I think it is still like intrinsically hard if we say, okay, in this inference, we can really know what goes wrong and then correct it. That's almost impossible, at least at this stage to me. But the good things from the model that you use is that we can evaluate how wrong that is. And for example, if we have 3 different models and we can compare how these 3 perform differently, and probably one of them perform better than other, and that help us conceptually correct the model error in a way. So that's just my thoughts. And I think, yes, you're right. The procedure I just described is pretty arbitrary and is sometimes just like let it work, and that's like the simple solution. But this is more like unified. Thank you very much for your presentation.
Thank you. I'm very foggy in my head, so it's hard for me to think through the exact things you said to understand. I'm sorry. I'm actually quite bothered by it. I shouldn't give a talk right now. But there was something else I was just thinking comes to mind too. Biggest hurdles of people using the now the thing is this is the issue. In the case of misspecification, we do not know the data generating parameters, right? We don't know their values, so I can never demonstrate that my procedure gets us closer to reality than the old procedure. So this is all based on theoretical arguments, statistics, law of large numbers, central limit theorem, all that makes sense. The statisticians agree on that's the way to do it. But we can never show that the estimates of uncertainty that we're getting that are statistically more correct, because we cannot measure the true parameters, right? If I could show that in the situation that I just described, the watershed, that the methodology with the sandwich corrector brings us closer to the true parameters, but we don't know what the true is. So that's another hurdle for other people to use it. But there's no benchmark, essentially. I mean, ultimately it will be benchmark based on statistics, but yeah, we can measure the parameters. Hoshin.
So first of all, Jasper, I really enjoyed that. Thank you.
Oh, thank you.
I'm sorry we hadn't had time to talk before this. I've just been busy. You called it a side issue, but of course it is the main issue, which is that your model is always going to be misspecified. So, and the whole power of this stems from the fact that your model is never going to be not misspecified, except in artificially constructed cases. Yep. So, so starting from there, the idea then is, okay, I'm going to accept the fact that I have a misspecified model, but I still want to be able to use that model. And so we're talking about practical application here, not so much about whether the model is wrong or right. We know it's wrong. And what does it mean to use the model? It means to generate estimates of the parameters of a misspecified model, to generate uncertainty estimates associated with that. And why do we need those uncertainty estimates? Because we want to be able to project that uncertainty in the estimation of the model into the predictions. And that's what you showed is that if you make the naive assumption, the comment I made earlier, your parameter variance will essentially go to 0 under the naive estimation, because that's the assumption of a true model. And when you have a misspecified model, your parameter variance should never go to 0, because you are accounting for the model error by burying that model error in the parameter error. You're sort of encoding it as errors in the parameters, or uncertainty in the parameters. So, so I think that's the interesting thing. And the other part that's slightly missed is that even after you estimate the parameters, you still have the variance of the residuals on top. So when you project your uncertainty into the output space, you're projecting both the uncertainty through the parameters plus the estimation of the residual model, right?
Yeah, that's the confidence and the prediction limits. Yeah, the difference
right,
between
that's
those
right,
two.
yeah.
Yeah, yeah.
Okay.
So I need to think back about this. That brings up whether these are only confidence or also include prediction.
So
yeah.
we know the I don't know which one you're calling prediction or confidence, but we know that the one due to parameter uncertainty is not required to bracket the data. It's only when you add the extra.
It's confidence parameters only.
Okay, sorry, the terminology, I get confused. So so
but
that's
yes, you're right about that, Hoshin. That's an important point. Yes, the parameter uncertainty doesn't have to cover the data, but they do have to. The coverage probabilities of those parameter intervals need to match their nominal counterparts from frequentist theory. But that is a side. That's a whole side thing.
Yeah.
Yes.
So it has, as you said, tremendous implications for correctly specifying the uncertainty of your model predictions, and presumably by accounting for this, you'll do a better job. One of the basic problems with glue is it always gave very wide uncertainty intervals on the base flows, and your graphs show very nicely that you correctly reflect the fact that the uncertainties are larger on the peaks and smaller on the variances. Okay. There are other interesting things that would be worth considering here. For example, if you have a correctly specified model in everything except for the fact that a parameter is changing with time. Take that as an example, right? So let's say all of the parameters are constant. This is again a synthetic example, but one of the parameters varies with a sinusoidal frequency of some amplitude, right? So in other words, the actual model has a higher parameter dimension, and the one you've specified has a lower parameter dimension. It would be interesting to know if the estimates for the parameters that are correctly specified are affected or not by the one that has been, in this case, misspecified by, it would be an interesting experiment for you to do. But my question, which I'm trying to understand behind your theory, is what is it that makes us confident that the limiting distribution can be described as a Gaussian? What is the fundamental argument?
Central limit theorem.
So we're arguing that the parameter estimates will never converge to anything other than Gaussian. Is that the argument here?
If you have an infinite sample, so what you will see in general, that the larger your sample size, right, the more Gaussian that target or posterior will be.
Okay.
And the reason why that is, there's all kind of law of large numbers, the central limit theorem, all that goes in there.
I thought it was large limit. I just wanted to verify with you since you've been into it. I'm curious about a slightly different situation then, since we're talking about it. So let's assume you have a model, a Gaussian, let's say a Gaussian data generating function, for which you've got the mean and the covariance. And now this is highly speculative, but I'm curious what you would say. Now I'm going to assume that my mean is actually generated by a log normal distribution. Okay. So the true parameters are really the parameters of the log normal distribution underlying the data generating process. But if you didn't assume that, you would estimate the parameters of your Gaussian distribution, and you would estimate your covariance of your parameter distribution. You would estimate that distribution as being Gaussian, where in actual fact it comes from some other distribution, which could happen in a data generating process, which is much more complicated, right? But you're representing it by a simpler representation. It just starts to boggle my mind a little bit.
Mm-hmm.
You start to consider something like that, yeah.
Mm-hmm. Yeah, so basically you have a data generating process where the mean of your data generating process is parameterized as a log normal distribution. Do you understand that?
Yeah.
I
Of course, I'm cheating because actually the parameters that I should be estimating are the parameters of the log normal distribution.
yeah.
Right? Yeah.
So
But
there, yes. Yeah, so this is a very important example, and the reason is we are always estimating parameters that are probably time variant because we don't know the right transfer function for that, like in this case, the premise of the log normal distribution, right? Because the mean is just a draw from that distribution. So that's why it's a relevant example. But what was your question again, Hoshin, related to this, whether the inference method would find that the parameters, that this is a misspecified
no. I'm just pointing out that the issue of misspecification is a very subtle one, right?
Mm-hmm, mm-hmm, mm-hmm.
You can misspecify parameters as being constant when they're actually time varying.
Yeah.
You can misspecify parameters as being fixed deterministic values when in fact they're actually the outputs of a distribution, right? But
Yes.
there's this trick that we play in the way we build models, where we say that things that are stochastic, that we're not able to specify, are specified by a distribution, and the distribution is fixed.
Yeah. Yes.
And so we have this peculiar way of dealing with uncertainty, where we take something that's uncertain and we represent it by something that's not uncertain.
Yeah.
And we do that because there's no other way to do it. I mean, we have to come up with a minimum description length representation of the system. The other implication that I'm wondering about over here is that when you go to machine learning, you have the possibility of building a representation, very high dimensional representation, but you have the possibility of building a representation. I forgot to mention, the other aspect is that your structure is misspecified, right? Not the parameters. And the more interesting problem is the actual equations are wrong, right?
Yes. Yeah. That's what I wanted to add to what you said, is that it doesn't only have to be the parameters. The inference method will.
Right. So when we get to
find
machine
that.
learning, we have the possibility that the machine learning model can, with sufficiently high dimension, approach a place where you cannot argue that the structure is misspecified. The structure is as close as possible to being correctly specified as possible. But the problem of the parameter, so it'd be interesting to see what happens to the estimates of the parameters as your dimension starts to approach, very large things as in machine learning.
So, Hoshin, if I have time and you're interested, maybe we can set up a few simple case studies and run both estimators to see if we can actually, because I also have to think back about, remember Peter, what's his last name now? That worked with Keith also in Lancaster.
Young.
Yeah, Peter Young, that looked at parameter variation as function of time with his instrumental, what is it called, variables or instrumental,
yes,
to actually smooth out that variation to arrive at a model that doesn't have parameter variation as your final approximation of a reasonable model of the system.
Another example is, sorry, Jonathan, let me just mention this. Another example is UWI has a student, Eduardo, who is using a classical hydrological model, which we know is misspecified, but he's estimating the parameters of that model as the output of an LSTM, which allows it to specify the parameters as being time varying, whereas of course your LSTM itself now has fixed constant parameters. So, you know, you have a way to maintain the interpretability of your physical model, but account for the fact that the misspecification of the fact that the parameters actually should be varying in time in order to give you the best representation. So you might want to talk to him too.
Yeah. Okay.
Jonathan.
Yeah, I was just going to mention, like, if you have some precise system with just a few, well, you can model it with just a few variables or a few parameters. It's not necessarily the case if the model structure is correct, because it's like a very simple low dimensional model structure, then you can get the correct parameters, and they wouldn't be misspecified, so you could approach that perfect model, right? It's only the high dimensionality where we can't get to the fully specified parameter set. Is that right?
Yes, but yeah. No, that's a good point. But I still think that even a low-dimensional system, if our representation of that system is wrong, then we cannot measure the parameters of this system directly, right?
If it's wrong, but if it's a very high, like a very precise system, just like a spring or something, we could represent the parameter very well.
If your model is a perfect representation of that low-dimensional system. I can think of systems that are relatively low-dimensional, but for which we may not be able to get a perfect representation. And so for which we can get a good representation. But basically, the point I was trying to make, and maybe you talk about something else, Jonathan, is that what is the reason for people not to use methods? In this case, is that the sandwich estimator, this procedure, we can never demonstrate that our estimates of uncertainty are more realistic, in essence, than the ones you get from other estimators. Yes, the demonstration is in the theory. That's all fine, but I'm talking about the practical application. If for some reason you can show that for a low-dimensional system, that this sandwich estimator describes the uncertainty in such a way that it still includes the data generating process parameters, because we were able to measure them directly, but we're not able to measure them directly. So there's no way of demonstrating that one estimate of certainty in that sense is maybe better than another, except then it's all based on theory, the sandwich estimator. So it's all finds arguments in Bayesian frequencies, that's all fine. But in practical application, it's maybe hard to, tell people, demonstrate, if you use the sandwich estimate, then yes, you get larger uncertainty. Yeah, you'll have data.
Is it possible to have two methods of uncertainty estimation that both produce ergodicity for a system?
I think so. Depending on the theory, they differ in their theoretical.
So that wouldn't be evidence of a correct uncertainty estimate.
No, because you can have it all depends on your underlying assumption. But anyway, that's an interesting question.
Part of the problem here is we're not being precise about what we mean by uncertainty. Yeah. So,
no, probably, yeah.
Yeah. So if I have a data set of length n, n samples from my distribution, let's say it's just simple Gaussian distribution. I've got n samples. Then the uncertainty associated with my estimate of the mean has to do with the fact that if I take repeated n samples many, many times, I will get different estimates for the mean. And I need to account for the fact that I've only got a single sample out a billion possible. In other words, I have to take into account data sampling variability associated with the fact that my sample is very short. I mean, to me, that's a more precise definition of uncertainty. So, so let me give an example. If I start with a deterministic, spatially distributed physical model, where everything is well specified, and I run the rainfall through the model, starting with correctly specified values for the parameters, correctly specified values for the state variables, and so on, and I generate values of stream flow. Okay, and I do this, and I generate an infinitely long sample. This model, which is perfectly specified, has no uncertainty, right? By construction, there's no uncertainty. If I now take a small sample of that and try to estimate those parameters, now uncertainty will arise because I don't know what the parameters are and I'm having to estimate them from a finite sample of values. Also, if I replace that physical distributed model with a lower dimensional model, that's now structural misspecification. So first one was just absence of enough data. Second one is structural misspecification. Now I say I take a lumped version. Now I'm going to end up with a situation where not only will there be uncertainty due to not the single sample and not infinite, but also now because I've now misspecified the representation. And so now I have to reflect that also in my situation.
Mm-hmm.
If you then go back to the original model and you have the parameters varying with time, which happens in reality, then you've got a third level, right? Yeah. So so part of the problem is that we have to, the reason why we have to reflect the uncertainty of the parameters is really those at least those two things, right? The structural uncertainty due to lower dimensionality typically, and also the fact that we've only sampled one realization of the observation.
Yes, you're right. And I just realized that, I didn't present it the way I wanted to, but that really requires the analytic derivation to really give people an understanding what is now the difference between that A and a B matrix, because they're basically estimators of the same thing. And that thing will be the same, those estimators, under conditions where the model, you don't have all these problems with misspecification. And so that's not too difficult to do, to give people to understand what's the difference between the two, A and B.
The interesting thing with the machine learning thing is that in principle, you could keep increasing the capacity of your machine learning model.
Yes.
Let's say we give it infinite data, you give it lots of data synthetically, right? And it would be interesting to know at what point, when you get to an appropriate dimension, the misspecification is so small as to not matter, right?
So, Hoshin, well, very good question before the. Do you remember that Peter made a remark where he said that in his experience and the people in the machine learning field is that if you use heuristics to do calibration training, that those methods may find better solutions for in-sample than gradient-based methods, but that those heuristics, that they don't do as well for out-of-sample, and that they didn't have a real understanding why was that. And I think, and that's what I'm going to think, I mentioned it, you were there, I think it is that gradient-based methods, when they compute their shift factor, right, they maintain structure between the parameters, because that's in the Jacobian, in the gradient. Whereas heuristic methods that sample independently don't maintain that structure. And that's why I think that those gradient-based methods do better in out-of-sample, because they maintain structure between the parameters, whereas heuristics may find a solution that's better in sample, but they distort the relationship between the parameters, so they may not do as well in extrapolation out of sample. They didn't have an idea. But anyway, point is, I just responded to that because you mentioned something similar about the structure out of sample, etc. Anyway, Pesci.
So I actually have a question to host actually because he mentioned about the uncertainty. I'm thinking, I mean, usually when we perceive the uncertainty is because of our limited knowledge associated with the system. But when we think of the dynamic system or the natural system itself, is this really a stochastic process or dynamic process? Suppose we, I mean, there's a God over there, he knows everything. Is the system deterministic or stochastic?
Well, this is the fundamental philosophical question of physics, right? You can either assume that the system is fundamentally deterministic, but you're not able to know everything, or you can assume that it's fundamentally stochastic. And I don't know if I'm not mistaken, you cannot actually distinguish between these using the tools at our disposal.
Because it's the reason I raised the question, because this I was thinking, like, if you think of like problem was once fancy about the evolution of the PDF, the density. So it's assuming that there's some uncertainty associated with the states. But if we assume the system is deterministic, but there's still some synergistic and redundant, effect evolve over time. But mathematically, where does this density comes from?
Well, you can make three assumptions, Peishi. You can assume that the system is completely deterministic. That's almost like the Newtonian approach to physics, right?
Yeah.
But that you cannot observe it. You cannot observe everything that you need to observe about that system. Okay.
Mm-hmm.
So you're representing it with a lower dimensional representation. And so that determinism, when it's projected from high dimensions to lower dimensions, appears to behave in a way that you don't know how to describe. So you describe it using probabilities or stochastic distributions. Okay.
Mm-hmm.
But this is a case where you're assuming that the actual real system was deterministic. Okay. The second possibility is that you can assume that the system itself is fundamentally stochastic.
Mm-hmm.
But you have to represent that stochasticity using a deterministic representation. By that I mean, you say that it's fundamentally Gaussian with a mean and standard deviation, but I have to specify the distributional shape, and that can only be specified deterministically, right? So I give
point
you.
of view, it's basically two different views of how we formulate the whole world, and
the third is a mixture of those two, where you allow for some parts of it to be deterministic and some parts of it to be stochastic, right? And the parts that are deterministic we think of as algorithmic information theory. You can describe them, you can compress it down, and then you get the distribution, and then everything else can only be described in terms of its surprise. Yeah.
then the follow question is, will these different views of world will give us the similar conclusions on like the scientific understanding? Say I want to see a multivariate interactions influence on like the future state and so forth. If we formulate the system in different ways, will this give us the same answers?
Yes and no. They will give us the same answers in terms of what we can measure, but our interpretations are different. Because our interpretations are inferences we make from what we can do, right?
Mm-hmm.
And we can never validate those inferences because those inferences are fundamentally baked into our priors, the way we view the universe.
Okay, thanks.
I think if you make your sample size large enough, that even if a failure will correct it, ultimately all those different views of the world will ultimately converge. But that may take, for each worldview, the sample size required may differ, probably.
You
Maybe.
mean they will all converge to a distribution? Or
Yeah,
okay.
so that lambda thing, and that's the interesting thing, that lambda thing I talked about that to be at the end related to clue, that's called the learning rate. And you can play with that learning rate. That's a way of dealing with structural error. And so writing as a follow-up, so there are you can play with the likelihood exponent, that lambda, because it doesn't affect the uncertainty, to tone down learning, to slow down learning in the presence of misspecification, so that they call it the learning rate. So that's the way of dealing with misspecification, effectively, going back to earlier question you asked. But anyway, that's a whole, so much work still to do on that, but anyway.
Actually, yeah,
but practically speaking, you have to represent an infinite dimensional universe using a finite dimensional model. You cannot do it any other way, right? Your representation always has to be part of the universe. So it always finite dimensional. So you're always projecting it down to a lower dimension. And so you always end up having to account for things that you don't know how to describe.
Yeah, I mean, yeah, all our models are reduce all the models.
Exactly.
Yeah, it's
You have to use a part of the space of the universe to represent the universe. Right? It's
important to get some feeling, right? What the effect is of your assumptions on your inferences. And that's why these methods are useful, because without doing any of this, people have no feeling. And to be honest, Hoshin, I never realized that the MCMC, that there is an assumption of a perfect model in there, because it's not intuitive. And that is the thing, is that we use inference methods all the time, that there are assumptions in there, but these assumptions are not clear. It's important yeah, anyway.
Well, I mean, we talked about this a long time ago, and I mean, Gray has also pointed to it that, you know, we have to specify the likelihood, the specification of the likelihood itself is imperfect. We've sort of been dancing around it, but now you're making it very explicit with your paper, and that's very nice. Yeah.
Yeah. I wonder what the editor is going to say. I fear it's too technical. Not the early part of the paper. Anyway, I've drifted a little bit more in the direction of everything I wanted to do. I wanted to be based on first principles.
The challenge is communicating it. The challenge is not that you haven't done a good job with your theory. The challenge is that's always going to be there. The challenge is always going to be communicating it. And your presentation was, I thought, an excellent communication. So,
thank you. I was so foggy in my head. Honestly, this was for me one of the most challenging talks I've ever done, because I wasn't clear in my head at all. I just came out of that procedures. I honestly thought at the end, oh, this was horrible. But anyway, I appreciate that. Yeah.
You're going to have to practice different ways of presenting it depending on the audience, right? So, yeah, audience of Vogel and other statisticians and so on, they will want a different presentation than.
Oh yeah. Oh yeah, they would have killed me today.
Than the classical. No, I think they would have been fine. I'm just saying is that the problem with communicating something like this is that you have to figure out how to adapt it to the audience. It has to feel intuitive to them, right? And so the way you introduce it and so on. Your simple example of the Gaussian distribution generating function and the misspecification assuming the uniform, I thought was excellent. If you could add to that another example, which is, a model. Well, you kind of have the ABC model, but something very simple like a regression model or something, right? I think that would probably help people make the leap between the statistical theory and the application. Yeah.
So Hoshin, I just got another rejection from NASA. Yeah. So how is this ever going to get funding, right? This type of, like, this is hard to get funding for this type of theoretical stuff.
Not from hydrology. I don't know if you can get funding from the statistical areas, because the reality is the earth sciences are concerned with application. They're not so much concerned with theory. You have to show a practical application, something to work. They're not going to fund you to develop the theory, which is why I gave up a long time ago trying to get any money out of them. But once you have it, then maybe you can get funding to demonstrate its implications. Yeah.
But it's quite interesting because the whole world is always waiting for a fundamental breakthrough, because that then opens up. You see, that's the irony of everything, right?
Yep.
It's anyway.
It's that thing about there have been a lot of complaints about the way science is funded, right? I mean, most breakthroughs are not made by huge teams. Most breakthroughs are made by individuals who question
Yes.
fundamental assumptions. Then the application breakthroughs are made by teams.
Yes.
But the fundamental things usually is some guy, sitting in his little lab somewhere.
Yeah.
Okay, guys, thank you so much for that. I've got to go
Thank you
to
for your
lunch.
time and attention, Hoshin and Young and everyone else. And Leila, thank you so much.
Love
Thank
to
you,
talk to you
Jasper.
some
This
more
was
about this, Jasper. I've been approaching the metric problem from a completely different perspective, but maybe sometime we'll have a chance to think about it. I think complementary to what
great.
we're talking about. Yeah.
You're great.
Okay.
You.
Bye,
Bye-bye.
Yang.
Thank
bye-bye.
you.
This
Bye.
was a great
Bye-bye.
presentation.
Okay,
Thank
Shi.
you, Jasper.
Thank you. Thank you all.
Bye-bye.
Bye-bye.